Hello, today we will talk about principal components analysis, or short PCA. I'd like to start with a cite from the suggested literature that says the following. PCA involves a mathematical procedure that transforms a set of correlated variables into a smaller set of uncorrelated variables. Those uncorrelated variables we called principal components. These principal components are linear combinations of the original variables and can be thought of as a new variables. Uses of PCA are multiple. Perhaps the most important is the one that we just mentioned, that is called dimension reduction. That is to represent the p-dimensional data, so the correlated variables, to q-dimension data, where this q should be smaller than our p, but to retain as much information as we can from the original data set, from the original p variables. We will see how to do that in just a moment. Other uses of the PCA are for data screening, to find outliers, or clustering, classification, regression, etc. So there are multiple uses. Today we will cover only a way to choose those q variables, those q linear combinations of our original variables, and how many should we choose, how many principal components or those uncorrelated variables we should choose. Obviously we do not want p principal components, as our original set has p variables. So we will consider population principal components and the sample principal components. First, what we want to do is derive a couple of results or theorems for the population principal components and applying them to the sample principal components. Geometrically, choosing those principal components is actually choosing a new coordinate system. So we rotate original coordinate system to the system of principal components. Let's first derive the population principal components and say that we have a random vector, so p-dimensional random vector. We have p variables with covariance matrix sigma and eigenvalues and corresponding eigenvectors. So those are our eigenvalue-eigenvector pairs. Okay, where we assume that lambda 1 is our largest eigenvalue and lambda p is our smallest eigenvalue. Consider those arbitrary linear combinations. So those could be our principal components. But what we said is that we want these principal components to contain as much information as it is possible for a linear combination of those vectors to contain. What it actually means is that we want the variance of this principal component of this linear combination to be as largest as possible. That is, we want to maximize the variance. What we know, we can calculate the variance of each of those linear combinations. We can also calculate covariances between those. We also mentioned that we want those principal components to be uncorrelated. So we want y1 and y2, covariance between those two, to be 0. As I mentioned, those vectors or those linear combinations, they're arbitrary for now, but instead we will consider vectors such that they have unit length. So the dot product of each of those is 1. So A1 transposed A1 is equal to 1. So the length is 1. And then we will maximize variance of each of those with that constraint, that the length of this vector is 1. Why we do that? Why do we need this unit length? Because we can always multiply the variance with, or this vector, with some constant, and we will get larger variance. So we need that constraint, let's say. So to get our first principal components, it is easy. So we just want to maximize the variance. and the variance of a vector defined like this, where x is our random vector, is A1 transposed, then covariance of x, that is our sigma, and A1. So it should look something like this, but instead of E, we have A. And then we maximize subject to A1 transposed A1 equal to 1. For the following principal component, we don't want just to maximize the variance, we also want the correlation between the first principal component and the second one to be 0. So we would want the covariance between those two, or equally those two, to be 0. So this is our another constraint, right? So how we would choose, and let's say P, how would we choose this? So we would like maximum variance, right? And covariance between all of previous to be 0. So y1, yp to be 0, y2, yp to be 0, y3, yp. So the covariance between each to be 0. So in that sense, they're uncorrelated. Okay, so this is the way to get all p components, but usually we don't want all principal components, all p. We usually want q that is smaller. How can we choose the principal components? So how many do we actually need to explain our original data set? We will see later. So let's see what choices of our vectors actually maximize this variance, and the covariance between those is 0. First, recall what we just said here, that we have our covariance matrix and this eigenvector eigenvalue pairs. So consider this for all theorems. Okay, so this is our assumption. Then we know that our ith principal component is given by this linear combination of our initial p variables, where this is our, for example, e1 is our corresponding eigenvector and lambda 1 is corresponding eigenvalue, and that eigenvalue, that particular one, is actually our maximum variance for this principal component. So not only that pair determines the linear combination, but it also determines the variance. So we know that variance of this principal component is going to be lambda I. Also, because those choices, E1, E2 to EP, are orthogonal, okay, so they're perpendicular mutually, we know that the covariance is going to be 0. So we just state those theorems without a proof, but proof follows immediately from the introduction class, where we actually said for what values we obtain maximum of the form, quadratic form divided by AI transposed AI. What we can notice from the very start is that these eigenvalues and eigenvectors are going to be through all of principal components analysis. So they play a really important role here. Next important result, or a theorem, that helps us determine the total population variance is this, that the sum of all our variances is actually the sum of all our variances of our principal components, and that is what we already know, because variance of yi is lambda I is the sum of our eigenvalues. In that sense, we can actually find the proportion of total population variance due to its principal component. So if we just divide, for example, lambda 1 with the sum of all those, we will get proportion for the first principal component. In general, this is one of the ways to determine how many do we want principal components. Usually we want 80 plus even 75 or more percentage of total population variance to be explained with first or how many principal components we take. So for example, if we have 5 variables and lambda1 plus lambda2 divided by this sum is more than 80%, then we will just take the first 2 principal components. Of course, there are multiple ways to decide how many principal components do you actually want. And you should always be careful how you choose them, but we will talk about that later. Before we go to the following theorem, where we have correlation coefficient between our components, principal components, and our variables, let's see what does this number represent. So this is from here. So what we can see here is that this number somehow measures the impact of this variable to this principal component. Okay. Moreover, this number tells us that the correlation coefficient, okay, is actually proportional to this number. Now, depending who you ask, some will tell you that you should only look at those numbers to interpret the principal components. Some do not agree and suggest use of this correlation coefficient. So again, this is our correlation coefficient between component, principal component, and our variables. Okay, and it is equal to, for example, if we look at first principal components, and this, so this would be E12, we would have E12 square root of our eigenvalue corresponding to principal component. So in this case first in this example, and then this would be a variance, or the whole thing would be the standard deviation. This is the standard deviation of our x2. So it is easy to compute this correlation coefficient. But always, in my opinion, you should choose to interpret all values that you have and take into consideration all information that you have. So both correlation coefficient and this number. So far we spoke only about our eigenvalue eigenvector pairs of our covariance matrix. Okay, let's instead consider standardized variables. So what does standardized variable means? For example, for z1, it means that z1 is equal to x1 minus its mean. Okay, so x1 minus mu1 divided by its standard deviation. So standard deviation of x1. That would be our z1. What we have shown is that the covariance of our standardized variables is actually going to be our rho, which is our correlation matrix of our initial variables. So if we consider now those eigenvalue eigenvector pairs of our correlation matrix instead of our covariance matrix, then we can again get some principal components that are in general different than the ones that we got here, because we now search for eigenvalue eigenvector pairs for our correlation matrix. In this case, we take of our covariance matrix. So we know how we can represent Z in a matrix form. So this is what we already have done. So we can find its covariance very easy. So what we gain by looking at the standardized variables is that the variance of each of those variables is 1. So from previous result, we know that the variance of our zi's in this case, okay, is going to be sum of our variances, and it is equal to 1 plus 1 plus 1 p times, so it is going to be p. Then from this equality we also know that sum of these variances is also going to be p. Then we can also derive this correlation coefficient, also because we know that this is 1, right? And the principal components themselves are easy to derive using this formula here. So here we just substitute our z in a matrix form. So this is z in matrix form. This is how we used to calculate it earlier. Now it is easier also to compute these proportions, so of population variance, in this case of our standardized variables. So just by dividing our, for example, first eigenvalue by p. So p is the number of our initial variables. We still are talking about population. So here we have population covariance matrix and population mean, everything. However, we had no assumptions about our random vector. We never said that it follows, for example, multivariate normal distribution. So in that case, it can be interesting. So a couple of interesting properties can be derived. For example, if you remember the ellipsoids, how do they look? And the vectors that we wrote, for example, we had 3 cases in one of our examples. Then you can look at that example again, and you can see how we actually transform that coordinate system from our p variables to our principal components variables. So why would we ever take, for example, principal components of our standardized variables instead of our initial variables? Well, in this case, those variables are scaled. So if we have some variable, for example, x1 has some large numbers in thousands, for example, and our second variable or any other has some small variable range, for example, 0 point something or 1, 2, and this is in thousands. Obviously, the variance of the first one is going to be much larger, so it is going to have much more impact on our principal components. In some cases, we want that impact to stay. Depends on what are we actually looking into. But usually, we want to eliminate that scaling, so we just standardize the variables and look to find the principal components of standardized variables. But again, it totally depends on the problem that you have. Next, let's go to our sample principal components and say that we have some, let's say, data taken from a population, our p-dimensional population. Then those linear combinations with maximum variance and that they're uncorrelated are the sample principal components. They're the sample principal because we obtained them using the sample covariance matrix or the sample correlation matrix. So if we have those pairs of our samples, so we have now with the hat, okay, then our each sample principal component is given like this. So those x1, x2, xp are those drawings from our population, let's say p-dimensional population. Okay, again we order our eigenvalues and corresponding eigenvectors. So now we know our sample variance, sample covariance between all that are different, or also our total sample variance. Those results are coming from the theorems before that we introduced, and our sample correlation coefficient given by this. The same results may be obtained if we, instead of our S of our sample covariance matrix, we consider our correlation matrix. But the question that comes here in mind is like which sample covariance matrix should we use, right? So in case that we use the maximum likelihood estimate of our covariance matrix, so divided by n, then we will have also maximum likelihood estimates of our vectors and our eigenvalues, right? So that is under assumption that our sample is actually from multivariate normal distribution. However, in the end, whichever matrix you use, you will have the same principal components. So because the eigenvalue will change, but the eigenvectors will stay the same. Also, the proportion is going to stay the same. So the total sample variance will change, but the proportion will stay the same. So if you are using, for example, R, there is a function there which uses not S but our Sn. So instead of 1 divided by n minus 1, it uses 1 divided by n. But you can always check this and choose whichever you want. When you're using the sample correlation matrix, you don't have this problem. So this follows immediately from the formula of our sample correlation matrix. So even if it's divided by n or n minus 1, it will still yield the same sample correlation matrix. So I mentioned the function in R, so I need to say about spectral value decomposition, single value decomposition, sorry. This is a decomposition that R uses to find our principal components. So we will not get in details about single value decomposition, but you might in some other courses mention that. Okay, so here we mentioned about one of the ways to choose how many principal components you want, but another way is called a scree plot. So that is a plot where on x-axis you have the numbers, so 1, 2, 3 to p, and on the y you have actually the values of the, in this case, sample. So these ones, sample eigenvalues. And you're looking at a pattern that is kind of like elbow pattern. So you will see this on problem solving. So this is another way, and where this occurs, this elbow, you know when to stop and how many principal components actually to choose. This usually gives the same result as you would choose by looking into the proportion of total variances. So you would usually choose the same number of principal components. So what I mentioned earlier is that if we take our maximum likelihood estimate, then, and under the assumption that our vector actually comes from multivariate normal distribution, okay, so in that case, our vectors and our lambda i's can be considered and as random variables, as maximum likelihood estimators. But to derive its distribution, it's really hard, so it is out of scope of this book and our lectures. So we will not talk about how to derive them, but we'll talk about assumption that actually none of them are equal, so they're all different. So this is important assumption for us, or for people who derived their distribution, so of our vectors and eigenvalues. So what we will do is to derive a test to see if the eigenvalues are actually going to be equal. So we will set up a null hypothesis such that our correlation matrix actually yields equal eigenvalues. So we will consider, let's see if I have it here, yes. So we will consider that our matrix rho is actually equal to this matrix. This matrix yields same, not distinct eigenvalues. Okay, and then our result for the distribution of these two will not apply. So one of the special correlation structures is this, and we would like to test that case. You should not expect such complicated test statistic on test. If you're given that, you will have all the information you need. So just know that this test statistic uses chi-square distribution. So this is just one of the ways to test equality of the eigenvalues, but under the special circumstances, special covariance structure. Okay, so this is it for the theory part. Thank you. Bye.